Hello class, welcome to our lesson today dealing with section 5.4. Today we're going to look at binomial distributions in a slightly different light. We're going to be looking at how to find the mean, variance, and standard deviation of those distributions. The formulas for the binomial distributions and mean, standard deviation, and variance are the following. To find the mean, you just take n times p. To find the variance, which remember we denote by sigma squared, is n times p times q, and standard deviation is the square root of n times p times q. Now, what we're going to be looking at today is a bunch of example questions about how to find variance, how to find standard deviation, how to find the mean, and then applying that to the whole idea of two standard deviations away from the mean to be considered usual or unusual. This gives us another opportunity to figure out what is usual or unusual versus the formulas that we use with the combination and then p raised to the n, or x and q raised to the n minus x power. So it gives us another opportunity and another option. I think a lot of students find a little bit more success on some of this binomial distribution idea because it's a straightforward approach as long as you know what the variables are representing. So this says I toss a coin 600 times, the probability of getting tails is 0.6 or 60%. So n is 600, p is 0.4. That means q would be p is 0.6, which means q is 0.4. So the mean is just n times p, so 600 times 0.60, and that would be 360. Standard deviation would be the square root of n times p times q, so we'll do the variance first. So n times p times q would give me 144, and the square root of 144 would be 12. You should not assume that the standard deviation is going to be a nice number very often. It is in this first case, just so it's easier to see. And I think one more that we have has a nice answer for that. But in general, it probably won't be such a good number. Would getting so many tails be unusual? The easiest way to do that with this scenario is to just do the standard deviation approach. So just take the mean, which is 360, plus or minus 2 of the standard deviation. So if we take 2 times 12, that would be 24. 360 minus 24 is 336. 360 plus 24 would be 384. So would getting 426 tails be unusual? Yes, because the 426 is outside of the range of two standard deviations. Now, we could have done the ideas from the previous section, but to figure out 426, I'd have to do at least 426. So I'd have to do 426 plus 427 all the way up to 600. And so it's much easier to just say, well, let's just do two standard deviations and figure out if it's unusual that way. Would getting 252 heads be unusual? Well, the first thing is you got to make sure it's tails. And so that would be 348 tails if you take 600 minus 252. That would not be unusual because that's within the two standard deviations of the mean. So this two standard deviation approach is basically what we're going to be looking at. So we're going to be finding a lot of means, finding a lot of standard deviations, taking plus or minus 2 standard deviations, figuring out what's usual or unusual, and then using that to help answer the question. Okay, final exam, 100 multiple choice questions. It has 5 possible options, so A, B, C, D, E. Only one of them is correct. And this is the complete random guess. So you didn't study at all. You're just going in blind. You didn't pay much attention, and you're just taking the test. So finding the mean would be the 100 times the 0.2, which I got by taking 1 out of 5. I could have written that as 1/5 as well. So I should expect to get 20 right if I just randomly guess. The standard deviation, square root of n times p times q, so 100 times 0.2 times 0.8, and that will give me 4. Again, this worked out nicely. Most of them don't. So just keep that in mind that you may have to round that a little bit for the standard deviation. We're getting at least 60 answers correct to be unusual. There's 2 ways to find that. One way is to do p probability of x greater than or equal to 60. StatCrunch can do this, but by hand that's a little bit more challenging to do. So for what we're going to be looking at for a test situation, probably just do the 2 standard deviation approach. So 20 plus or minus 2 times 4, which would be 8. So that would be 20 minus 8, which is 12. 20 plus 8, which is 28. And so is 60 in that range? No, and anything from 60 on above is not in that range. And if you think about it, that would make sense as a teacher. If you have not done well or you didn't study and then you somehow pass the test, well, maybe you're just good at the subject and you didn't have to study as much. But it would be kind of surprising if you come to me and say, man, I just guessed on all those and I got at least a 60, so something might be up there. So that's something as a teacher that we would look at. But you should not expect to get a good score at that point. So 60 would be definitely an unusual answer. Okay, this says a test of a fair coin. So if it's a fair coin, we're going to assume that heads and tails are the same. So P and Q would both be 50%. Okay, N is 152. Now this 127 isn't needed until later. Okay, so we'll use that 127 in a little bit. So assuming the likelihood is the same, find the mean and standard deviation. So that'd be 152 N times P, which is 0.5, and that's 76. Standard deviation would be N times P times Q, and then square root it. That would be square root of 38, which I get about 6.16. Is getting 127 unusual? Well, if I take the mean plus or minus 2 standard deviations, I get a range of 63 up to 88. 127 is unusual, so it's outside the range. So what this probably means then is the coin wasn't a fair coin, or something happened with the toss. Most likely it's the fact that the coin is weighted one way over the other. And so 127 and 152, that would be 127 is an unusual amount. So that probably means the coin isn't fair because we got an unusual answer for that situation. The next question has a lot of info. So this is the idea if you've ever dealt with genetics, the Mendel experiments with genetics, and a lot of times they were with the stems or the pea pods being green or yellow. Those type of ideas we kind of looked at a little bit before, but they show up here again. So N is 1,064. There were this many samples that we were looking at. 787 have long stems, 277 short stems. The theory was 25% would be short stems. So this 25% is what we're going to use for P. We'll deal with these other numbers later. So 25% is P. Okay, if he was correct, find the mean and standard deviation. So N is the 1064 times P, which is 0.25, because I'm looking for short stems, and that'd be 266. Square root of N times P times Q, and then square root that answer, the square root of those three numbers multiplied together would be 14.12. So the mean, 266, that's what I should expect to occur. Okay, remember expected value is the mean. And then standard deviation is 14.12. If I do this mean plus or minus 2 standard deviations, I get around 237 up to 294. So is 277 unusual? It's not unusual. And so here's where you got to be careful. We can't prove that Mendel was correct about 25%. It could be like 26%, or it could be 24%. What we can say is, well, I can't say it's different than 25%. I don't know. Okay, but whatever that was said about the theory of 25%, I can't dispute that it's incorrect. I can't prove that it's true. Okay, but in statistics, we typically can't prove that things are true. We just say, well, I can't disprove you. Okay, so I can't say that the 25% is incorrect because your experiment had around 25%, because it would not be considered unusual in terms of this question. One last thing that I want to look at is just looking back at expected value with the lottery ticket idea. So this is a pick 7 game. So I got this 10 million number by taking 10 to the 7th. That's where this 10 million number comes from. So expected value for anything like this is probability you win times the amount of money you win, plus the probability you lose times the amount of money you lose. Okay, so the probability I win is just 1 out of the 10 million. Now I don't win 500,000. I win 500,000 minus the 75 cents. So 1 out of 10 million times the 500,000 minus 75 cents, which would be 499,999 and 25 cents. Then plus 9,999,999 out of 10 million, everything but the one way to win, times negative 75 cents, because if I spend the money and the 75 cents and I lose it, well, it's just gone. I've lost that 75 cents. My expected value should be a loss of 70 cents. Now, when you have expected value, make sure you realize I should expect to lose here, and that loss of 70 cents is what I should expect to occur. The one person that wins, okay, offsets the fact that the rest of us lose, but you shouldn't expect to get rich off of this situation, because you should expect to lose the 70 cents. You need to be able to explain a question like that. Make sure you can get it set up so it's probability you win times the amount of profit or the amount of money you win, plus the probability you lose times the amount of money you lose. And remember, these expected values should be negative. If the expected value is positive, that means the company putting out the lottery would have to shell out more money than they would bring in. So expected values in these situations should be negative as you're looking at them. Okay, just to review, make sure you know how to deal with the mean and standard deviation approaches with these formulas. You should be able to find N, P, and Q and then plug them in. This idea is a lot easier for larger samples compared to what we looked at in section 5.3, where we're just finding small amounts of data and small amounts of successes versus the total So you want to be able to use that idea and use the two standard deviation approach to prove if something is usual or unusual for this situation. Have a good day, everyone.